Hey everyone, sorry about the delay. Today we're going to be dealing with prime factorization, GCD, and LCM. The remainder of the notes will all be in one giant section and they will be posted uh, shortly by tomorrow morning at the latest. But for now we're going to be focusing on this stuff and on we go. So we'll start with factors, and what I mean by that is that they're a feature of a whole number that we can talk about to describe that number specifically. So let's say we have some number, we'll call it n. When we divide it by a number k and get another whole number, then we say that k is a factor. In more specific examples, we might say that 6 is a factor of 120 because 120 divided by 6 is 20. And 20 isn't so much the important thing as much as just 20 is a whole number. 120 has a lot of factors. You can see all of them there. And actually they come in pairs. So in the same way that 6 is a factor of 120, well, if I had divided 120 by 20 instead, I would have gotten 6. So you'll notice that this like pair-like relationship. So 1 and 120, 2 and 60, 3 and 40, 4 and 30, so on and so forth. Another way to think of factors, in fact, is if I can multiply these numbers and get the big number, then we would also call them factors. So let's go into factorization. So if we know the factors of a particular number, we can factor the number into smaller terms, which we can use for algebra purposes or some such nonsense like that. So we talk about something like 104. Well, we know that 4 is a factor because 104 divided by 4 is 26. And we can rewrite this relationship as 26 times 4, which is still 104. We call this a factorization. That's pretty much all a factorization is. So before we get into prime factorization, we should probably talk about primes. So let's talk about a number like 120. Well, 120 happens to have 120 as a factor. In fact, this isn't specific to 120 in that every number will always have itself as a factor. So 23 has 23 as a factor, 6 billion and 12 has 6 billion and 12 as a factor, so on and so forth. Guaranteed factor. And then in a similar note, the number 1 is also a factor for every number because any number divided by 1 is just itself. So if you start with a whole number, divide by 1, you'll end up with a whole number. When a number has exactly 2 factors, that's 1 and itself, we can call that number prime. And I should point out that the number 1 isn't a prime number. It only has one factor. You can count them, but in the case of something like 3, 3 happens to be prime. 3 has 2 factors, 1 and 3, so that's 2 factors, whereas 1 just has 1. We can think of a prime number as a number that can't be split up by factorization. So how do we find them anyway? Well, we can check if a number is prime. Let's take a slightly larger number than something like 3 or 7 and talk about a number like 127. Now, we could just check everything. 127 divided by 2, 127 divided by 3, 127 divided by 4, 127 divided by 5. This would take quite a long time. Notice we don't need to check 127 divided by 1 because we know that that works, and 127 divided by 127 is also fine. But if we're checking prime, we want to check the values that aren't 1 or itself. But that's still quite a bit of time. But remember that these factors come in pairs. So if you've got 2 factors that aren't the exact same, we're going to have a smaller factor and a larger factor. And what this basically means is we don't have to check the larger factor. So what I mean by this is that if you have something like 100, uh, you could say that 4 and 25 are factors, and they come in that pair because 4 times 25 is 100. Uh, if I know, if I want to find 4 and 25, I can search for just the smaller piece, which is the 4, and that's enough. Uh, so here's how to apply this in practice. So instead of doing all the way up to 127 divided by 126, we'll stop at 127 divided by 12. Now, uh, these numbers over there, which might take a little bit of time, none of them are whole numbers. You can check with a calculator. And more importantly, 127 divided by 12 is about 10.583, and that's smaller than 12. Uh, and the reason I say this is that that means that if we keep searching, we say divide by a bigger number, then the corresponding pair, if it did exist, would have been checked already. So since we checked all of the possible small values, we're kind of done. By the way, if you're curious on exactly when to stop, it's just going to be at the square root of the number. So right after the square root of the number, you can stop checking. In practice, this is pretty quick compared to checking everything. So worth noting. One of the things that we can do with prime numbers is we can constantly factor until we get prime numbers, which is to say that we can take two factors of a number, and if they're not prime already, we can break them apart further and then do the same process over and over again until we get nothing but primes. So that we can talk about a number as just a bunch of primes multiplied together. So take a number like 120. 120 is 20 times 6, but 20 isn't a prime number and 6 isn't a prime number either. But that's okay because we can factor our factors. And we can say that 6 is 2 times 3. 2 and 3 happen to be prime numbers. And we can also talk about 20 as 4 times 5. Now, you might know that 4 isn't a prime number, but we can break that apart even further to 2 times 2. So instead of saying that 120 is 20 times 6, we say 120 is 2 times 2 times 5 times 2 times 3. And we can rearrange the order of these things. So we would probably just say 2 times 2 times 2 times 3 times 5. We always go from like smallest to greatest. So how do we do this factorization? It's pretty simple. First step, check if it's prime. If the number is prime, we're done. We have nothing else to do. So in the example, I can give a prime number, 29, and the prime factorization of 29 is just 29. There's nothing special. If it's not, then we can write it as the product of two factors that aren't 1 and itself. So divide it by a number that isn't 1, and you'll get the second number. And then you repeat this process on both of the individual factors. So we might have to do this again and again and again on the individual terms. When it gets to really big values, you might have to repeat this several times, but that's okay. The order of these is always going to be from least to greatest, and because it's a little bit cleaner, we're going to use exponents rather than just saying the same number multiplied by itself several times. Let's do this with a pretty big number, 1820. So 1820 divided by 10 is 182. That means that 10 and 182 are factors. So we can rewrite 1820 as 10 times 182. By the way, 1820 has a bunch of factors, and if you picked a different pair, that's okay. Another example you could pick, for example, is 2 and 910 would work as well. In this case, though, we're working with 10 and 182, and you'll notice that 2 is a factor of both 10 and 182. So I can rewrite 10 as 2 times 5, and I can rewrite 182 as 2 times 91. Now, 2 and 5 are pretty easy to check that they're both prime, but is 91 prime? We have to check by dividing it by these smaller values in the calculator. And by the way, it's not. 91 is not a prime number. It is divisible by 7. So, and you don't have to check, remember, you don't have to check everything. You can just you can keep checking up until you start realizing that you are dividing by the bigger of the two numbers. So, 91 divided by 13 is 7. So so we know that 13 is on the bigger side. Right. 13 and 7 are prime, though. So we can rewrite that as the 2 times 5 is still there, but now 2 times 91 has turned to 2 times 7 times 13. And we can rewrite this with the exponents 2 squared, because we have two 2's, times 5 times 7 times 13. And we're done. And that is a prime factorization. So on to greatest common divisors. Okay, so remember, all positive whole numbers have a factor of 1, and since that's the case, we know that everything that's a whole number will have a factor in common with other whole numbers. In this case, it's 1, but maybe it's not the only one. In this case, the largest common factor, we can call that, is the greatest common divisor or greatest common factor. We often say GCD rather than GCF, but they both mean the same thing. So we can talk about something like 36 and 52. And we check all the factors. And so in the case of 36, 1 is a factor, 2 is a factor, 3 is a factor, 4 is a factor, 6 is a factor, 9 is a factor, 12 is a factor, 18 is a factor, and 36 is a factor. And the factors of 52 are 1, 2, 4, 13, 26, and 52. Now, obviously 1 and 2, well, those are all both clearly in common, but also 4. And if you check everything else, there's nothing else that these lists have in common. So we say that the GCD of 36 and 52 is 4, because of the three numbers that we circled. 4 is the biggest, and that's the GCD. The other thing we should probably mention is the least common multiple. So instead of talking about the factors, which is splitting up the number, a multiple is when I multiply the number by a whole number. So 1 times the number, 2 times the number, 3 times the number, 4 times the number, and so forth. You have an infinite number of multiples. And just like the factors of a number, we can actually check for common multiples between two different values. And fun fact, for any two whole numbers, there's a least common multiple. So you're not going to be looking forever. The smallest of these multiples is going to be known as the least common multiple. And we can talk about something like 15 and 20. So the multiples of 15, well, 15 times 1 is 15. 15 times 2 is 30. 15 times 3 is 45. Times 4 is 60. Times 5 is 75. Times 6 is 90. Times 7 is 105. Times 8 is 120. Times 9 is 135. And I can keep going, but the pattern is unnecessary. Now, the multiples of 20, however, are just 20, 40, 60, 80, 100, 120, 140, so on. Now, again, just like in the previous case, we circle the things that they have in common. In this case, if we wrote out literally all of the multiples, because there's an infinite amount, we would be doing an infinite amount of circling. As you see that this pattern repeats every 60. So 180, by the way, is a factor of 15. In this case, however, because the smallest value to be able to be circled in this case is 60, that's the LCM of 15 and 20. So people always like word problems, so let's give an example. We'll say that Martin has a 45-inch plank of wood, and he's got another 81-inch plank of wood. He wants to cut all of the planks into different pieces, all with the same length. What's the greatest length possible for these individual pieces? So we're dividing these pieces of wood into smaller pieces, so we're looking for factors, not multiples. If we were building multiple planks of wood together, that would be a multiples kind of problem. But we're dividing them, so we're looking at factors. The factors of 45 are just 1, 3, 5, 9, 15, and 45. Again, you check these by doing a bunch of division and seeing what works. And remember, they come in pairs. And the factors of 81 are 1, 3, 9, 27, and 81. Well, notice that I've put in bold already the stuff that they have in common, but the largest one they have in common is the 9. In the case of 45, 45 divided by 9 is 5, and in the case of 81, 81 divided by 9 is 9. So in this case, the largest length for these individual pieces, assuming I want to cut them all at the same length, is going to be 9 inches. And that's it. So let's give a different word problem. We'll say that Jonah can jog around a track in 14 minutes, but Emma's a little faster. She can jog around the track in 10 minutes. So let's say they start at the same location at the same time and they don't slow down for some reason and they run potentially forever. How many minutes before they complete a lap at the same time? So in this case, we're looking at multiples of laps. Like, for example, we definitely know the answer is at least 14 because Jonah finishes a lap in 14 minutes. So we're looking at a multiple of something, not a factor. And in this case, it's much bigger than 14. The multiples of 14, by the way, are 14, 28, 42, 56, 70, 84, 98, 112, 126, and 140, so on and so forth. The multiples of 10 are 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, so on and so forth. And notice that 70 is the thing they have in common. So we know that 70 is the smallest multiple they have in common. So assuming that they don't slow down, that they started at the same time, that they always keep the same kind of rhythm, they don't take breaks, that kind of thing, well, they're going to finish at 70 minutes at the same time. And while this wasn't asked, you could say that Jonah will have finished 5 laps, because 14 times 5 is 70, whereas Emma will have finished 7 laps, because 10 times 7 is 70. Either way, that will be it. I know that this is kind of short. I'm going to say again that the notes, the rest of them should be posted at the very latest by tomorrow morning. I know that this is kind of a slower than I normally put these out, and I'm sorry about that. If you do have questions about this or the sections that aren't in this exact section, please email me or message me through Canvas. I promise to get back to you as soon as I can. I've been a little bit caught up with some technical difficulties, hence the delays for this. And with that, other than that, I can say have a nice day.